Hello, and welcome to this short video where I will be presenting an update about the work that we have been conducting in our research team, Team 2, under the Circular Chemical Center. This slide is a quick reminder from our previous video. Theme 2 is concerned with process integration and all systems optimization. Our work builds on the catalytic technology innovations from Theme 1, following either of the waste recycling routes or biomass routes or CO2 utilization routes. It considers scaling up and integrating these recycling technologies into industrial processes and existing chemical supply chains. And the work aims to assess their economic performance and environmental and social impacts by adopting a life cycle view. The quantitative assessment that we are conducting relies on process and supply chain modeling, and it feeds into the work that is conducted under Theme 3 on financing a chemical circular economy and enabling new policy on the circularity of plastics and other chemicals. A majority of the work we are conducting or have been conducting so far under Theme 2 has been under Task 2.1, where we seek to identify the best routes for chemical recycling of solid waste, biomass, and CO2 streams into fresh olefins. Best routes in the sense that we want to minimize the production costs, but at the same time, we also want to minimize the environmental impact in terms of consuming less fossil resources or releasing less greenhouse gas emissions or greenhouse gases. Now, moving forward, we are starting to look at the deployment of these chemical recycling technologies, considering, for instance, their integration into existing chemical clusters. And my next slide will now show a bit more about our methodology and then some of the case studies we have been working on. This slide is a bit technical, and it tries to provide a high-level summary of a typical methodology that we use to assess and to compare chemical recycling technologies. Because many of the technologies we are interested in are at an early stage of development, an important element of our methodology is the development of detailed process models that can be used to predict the performance of a new technology at industrial scale. And for this, we are relying on lab scale or pilot scale data, of course, when they are available. And we try to take advantage of commercial process simulators such as Aspen HYSYS or GPROMs, which include a comprehensive databases of thermophysical properties of various chemicals. Now, having those process models allows us to conduct preliminary costings of the technologies by accounting for both capital and operating expenditures. Taking the case of ethylene production, for instance, this approach allows us to determine a levelized cost of ethylene production using a consistent costing methodology across different technologies. In a similar way, we can combine the process simulator results at scale with supply chain inventory data that we can retrieve from databases such as EcoInvent in order to assess the life cycle impacts of these technologies. So these impacts may be at the midpoint level, for instance, represented here, which includes greenhouse gas emissions, water use, or fossil resource consumption, or they may as well be further aggregated into endpoint damage areas which, for instance, relate to damage to human health or damage to resource availability. We may also conduct a more absolute sustainability assessment by considering the planetary boundaries in order to quantify the share of a particular industrial sector, or we may also seek to quantify the impacts of an activity on particular sustainable development goals, such as climate action or sustainable development and production. Now, most of the research that has been conducted under Theme 2 so far has been in connection to sustainable and circular ethylene production. We have looked at four main areas. First of all, considering the current state of the art, which is based on steam cracking of naphtha or ethane, we have looked at the potential of either full or partial electrification of ethane crackers. We have looked at the potential of fuel switching to hydrogen. We have also looked at the potential of integration with carbon capture to reduce emissions. And one interesting finding here has been that electrified crackers do have a high potential for heat integration and therefore higher energy efficiency, which is quite counterintuitive. Other assessments that we have been conducting are comparing the biomass route with the solid waste route to ethylene. One key finding here has been that depolymerization of ethylene using, for instance, fast pyrolysis could be economically competitive with conventional steam cracking, and could at the same time could significantly reduce the environmental damage that is caused by conventional steam cracking. We have also looked at the area of carbon capture and utilization by comparing various thermocatalytic and electrocatalytic routes to ethylene, starting from all the way from water and carbon dioxide. And what our assessment has allowed to confirm is that is about the environmental benefits afforded by electrochemical processes, yet at a significantly higher production cost. And of course, the electricity demand to meet the current ethylene production is rather staggering, as one might expect. Now, at this point, I feel it is also important to reiterate that a common trait among all these different techno-economic and environmental assessments is that they all rely on the same methodology, a consistent methodology, and the results, therefore, can be compared directly with one another. And clearly, one area for collaboration for us that we're interested in is always to complete this assessment of sustainable olefins production routes with new promising emerging technologies. I will finally conclude this presentation by trying to give an update on some of our future research plans in the area of chemical recycling, and also by saying that we are certainly interested in developing partnerships for these projects. The first direction that we want to explore further is in connection to chemical recycling of mixed plastic wastes, where we are more particularly interested at this point in advanced gasification technology in order to produce high-grade syngas as a key intermediate to hydrocarbon products. The other direction that we are considering is regarding the deployment of chemical recycling technologies, in particular, the deployments as part of existing chemical clusters. And as just one example, the Teesside cluster, we believe represents an excellent opportunity for greater industrial symbiosis and circularity, since it encompasses the production of key chemicals such as ethylene, acrylic, plastics, fertilizers, to name just a few. So with this, I wanted to say thank you for watching this video, And please feel free to reach out to me for further information if you're interested in our work.